Today lecture we will start a very important topic, which is the interaction of the electromagnetic radiation, light, with the atomic and molecular system. That is the basic of many things. First of all, in terms of nature in general, that's the way that life exists on the planet, is thanks to the interaction of light with atomic system, with molecular system, providing energy, transforming electromagnetic energy into chemical bond. We saw in the last lecture that in a molecule we have tenths of electron volts in the chemical bond. That's a lot of energy, you know, and this energy is what moves us around, is what makes the plants to grow, is what makes almost everything to take the course when we're dealing with life. But we did not really explore yet the concepts, the basics, what is involved, what are the fundamental mechanisms that makes light to excite, makes light to store energy in the atomic and molecular level. Okay, so and beside that, we have most of the techniques that we use for in biomedical science, techniques for like making exams or making detection, making diagnostic. Most of them use molecules that have a special behavior when interacting with light. So we can somehow identify things by looking the light that they emit, right? So this is a very important topic, and we're gonna cover slowly because you know, we could do a hand wave type of explanation, and we're going to do, but that's not enough. In this course, we want to go a little deep too, and we have to show you how things goes, what are the basic phenomena that takes place. And of course, I mean, we're going to go in some detail, but not deep enough that will take us a lot of time. But you get to understand, you know, how the quantum nature of matter, quantum nature of the atom and molecules, how the fact that energy is discretized, how the fact that spatial charge distribution given by the wave function square somehow is important in this context of interaction with light. So that's what we're going to do. Okay, so the topic today then we can has as a title interaction of electromagnetic radiation with the atomic system. And I already explained to you how important it is to understand this. And as I said, there are many things that we use in the daily basis that depends on that. Everybody in the field of biomedical or even engineering, they already saw things related to fluorescence. Normally, we can make molecules that sticks in the right place, and instead of looking directly to some cell or to some event that's taking place inside the cell or in a tissue, we look at the fluorescence of those markers. And that's light matter interaction, right? You know, you have to send light, you have to collect the light that comes, and through that we can identify things. There are techniques like Rama Spectroscopy. Rama Spectroscopy is very interesting. You know, we send light, the light goes, you're going to interact with the charges, we're going to interact with the electrons, but then you make the nucleus to vibrate. So you access what we call the vibrational levels, as we saw in the molecule. Therefore, we can identify things there. Or even absorption, just seeing the light disappear and transforming in other things, like chemical reaction, or just being scattered to other places. That's what we call absorption. They are important phenomena. I could list many things, but one of the applications that we're going to see in biomedical engineering are those techniques. So that comes after we can end this basic part of the quantum concepts. Before we start to deal with the electromagnetic oscillations in the atomic and molecular system, it will be nice to take a look and remember how is the electromagnetic field, right? And then remember the atomic system. We just saw it some lectures ago, so we are very fresh on that topic. But you have to understand that the nature of the electromagnetic radiation is electrical field and magnetic field. And the nature of the atomic and molecular system, you know, we have charges there in a special configuration. So electricity and magnetism love charges. That's why we have a strong interaction of the electromagnetic radiation with the atomic and molecular system, because they are made for each other. One is the field, the other is the charge, and they interact very strongly, as we learn in basic electricity and magnetism. Therefore, this is the basis of things. When the electrical field finds an atom, it sees the electron cloud as a charge distribution that will somehow transfer energy to it. We will make force on it. And by making this force, we will have a displacement of this charge distribution. And have a displacement of this charge distribution, it may cause that the system is in a normal configuration. That's one of the quantum states. But because of the interaction with the electromagnetic radiation, it can transform itself in another of possible state, quantum state, because as we saw, there are many electronic waves in the atoms, which are the distribution, which are the orbitals, which are the charge surrounding the nucleus. And the electromagnetic radiation can change that. And that's why we call transition. You know, putting the external electromagnetic field, we can cause the charge distribution to modify. We did not talk yet about the spin of the electron, but in that cloud, there is also spin of the electron. When you have a single electron, the spin is important. We're going to see some transition, but when we have two electrons, the spin became terribly important. And the magnetic field spin, as we saw, is angular, intrinsic angular momentum in the electron. And that's associated with a magnetic momentum. And the magnetic field interacts with that. So it can cause this modification of the spin state. So all that is in the topic of interaction of radiation with the atomic system. Now, we have to understand that when we speak about electromagnetic radiation, we are talking about fields that oscillate in time. So everything we learned so far, we did not include a lot of the time dependence on the states on it, because it was not necessary. Up to now, we were very much interested to see the stationary states, the steady state of the quantum system. So we are very interested to see how is the spatial distribution of the electronic cloud. We were interested to see if if a flux of electrons could pass through a barrier, you know, tunneling and that kind of thing. But now we are in a situation that the time variation of the electromagnetic field, which is essential, right? To have radiation, you need to have time and spatial variation. Periodically variation with time and with space, which somehow give us the wave number, the wavelength, and the frequency for the electromagnetic radiation. So we cannot forget the time now. The time dependence in the quantum system became essential, because that's what's going to give us the property. That's what's going to give us the way that the electromagnetic field can act. Okay. said all that, let me make a small review of the electromagnetic fields. So I know that everybody knows about. We're going to have to need to use the right notation so we can somehow progress well with the mathematical results that will consolidate or picture of this interaction of the electromagnetic field with atomic and molecular system. Very well. Well, first of all, the electromagnetic system, as we know, is a composition of two fields. So we have an electrical field, and as any good field, this is a vectorial field. So it has a vectorial sense. It has a vectorial characteristic. And we have the magnetic field. As any other good field, we do have also a vectorial type of dependence. The electrical field, normally oscillates in a direction. So we fix this direction. It can rotate as well. And that characterizes what we call polarization. So polarization is the spatial direction of oscillation of the electrical component of the electromagnetic field. Normally when the electrical field is oscillating in a plane, that is the plane of polarization. And that's essential because we're going to, in the first approach, consider the electromagnetic field oscillating. As the electromagnetic radiation propagates, the electrical field, which is here in this direction, right? This is the E field, this is the B field. They are perpendicular, as you can see, right? There is a constriction or a restriction in the electromagnetism that shows that. And a perpendicular, we have, as I said, the magnetic field oscillating. So as the things propagate in space, these things oscillate in time and space. So if I take a picture, I see this growing and coming down, invert, come down again. So actually the field, the electrical field is going up and down. So we gave here a direction, but actually this is going up and down in this direction. So the electrical field is going up and down in this direction. And the magnetic field is going right and left in this direction. So these things oscillate, right? And together with all that, they have a direction of propagation, which normally is given by the E cross B direction. So this is E cross B. So that E cross B, in fact, is the quantity of, is the flux. It's called the Poynting vector, and give us the direction of propagation of the electromagnetic field. Okay, now, this is essential for the electromagnetic radiation. It's the composition, it's these two fields, because all the interaction, there is no magic of the light interacting with the atomic and molecular system. The magic is that the atomic and molecular system are made of charges, distributed, and the radiation is made of electricity and magnetism, and they interact. So that's the whole thing about this interaction. And of course, we have to know how to deal with that in a good sense. Okay, so this is essential concept. Always we see light now. We need to see the fields. In your mind, light is the oscillations of those fields. I know that we're going to go to the photon kind of contest in the radiation too, because we have to understand a little bit about spontaneous emission, right? Stimulated emission and absorption, but at the moment we keep it with this in mind to understand. Normally, the electrical field, it can have different spatial profile. Of course, when it propagates, oscillates in space and time. So if I fix a position, right? In the space, let's say this is the z direction where the things are propagating. We have the two fields. And if I freeze, I see the spatial variation. But if I keep myself in one point, I see the time variation of the field. The time variation is always like a cosine and sine. So normally it is a harmonic type of oscillation for the time. But the spatial part, it can have different configuration. You may have a different distribution of the light, even though the main component of the light is a plane wave. So we have a spatial and a time dependence, and this is a combination of sines and cosines. And in the very beginning of the course, I made a small revision about waves, so you could always be familiar when I put expression like this. So that means something that oscillates in time and space with some velocity, typical velocity, which is basically, the omega divided by k, because you get a wavefront propagation, right? I explained that, I remember well. So the E and B field, in principle, they have this spatial and time independence, and that will be important for us. But the amplitude can also be spatial dependent. So we may have many situations where this amplitude depends on R, depends on space too, depends on position, right? And that gives us a lot of possibilities, Everybody already hear about Gaussian beam, about plane wave. This is a plane wave propagating, but there are many different waves. Sometimes it's not only spatial, but it's also time. It can rotate. This is different type of polarization. And sometimes it have a very interesting profile in space, spatial modes, depending on how the light is produced, right? And the same with B. So not only E, but B. Always E and B, they are connected through the Maxwell equations, right? We have a couple of equations, which are the Maxwell equations, that characterize very well the electromagnetic field. So this is first, I'm expanding some time, because this is very important. And you have to understand that there are some scales involved. In terms of time, the time scale is the inverse of this frequency. The inverse of this frequency gives us a time scale, which is the time for the field to go revert, get reversed in direction and comes back to the original direction. This is the time scale of oscillation of the electromagnetic field. That somehow has to couple to the time that something can happen in the atom. Because this field is going to go up and down. We must know what that means in terms of energy in the atom. Remember, any frequency means energy. We always deal with frequency, but we worry that any frequency following the quantum concept represents energy. H bar times the frequency is the energy. Okay. Then, there is a spatial scale. The spatial scale is the inverse of the k, which is the wave vector. We put here the wave vector again. So this side we have the wave vector, and this side we have omega, which is the frequency. Those are the two fundamental things we have to worry about. One deals with space, and the inverse of k gives us on the order of lambda. And lambda is the spatial kind of scale to see variations in the electromagnetic field. But remember, lambda can be very big, It can be like a micron. If you talk about the visible light, for instance, lambda for visible light is about a micron. And this is much, much bigger than the atomic distribution of the electron cloud in the atom. The electron cloud in the atom is on the order of the Bohr radius, which is on the order of angstrom. But here we deal with something that's many, many times more. So we have to see that the spatial variation and the time variation will couple to the electron cloud in different ways, because that will depend how is the ability for the atomic or the molecular electronic distribution to respond to those stimulus. Okay, so we are, again, just for completeness, we are in the wave picture. So this is a classical view of the electromagnetic radiation. We're gonna be able to transform this in photons number and things like this very soon. But we are now dealing, which is the easiest way to characterize this coupling of the electromagnetic radiation with the atomic system. So we are dealing with the wave picture. But the atomic system will be fully quantum. And because this is a classical picture of the radiation, we call what we're going to do at the coming moments of this lecture and the next lecture are related to what we call semi-classical light atom interaction. Okay, but we're never going to forget the photons, because we're going to need them soon, right? We're going to need them soon. Okay, so the first thing we would like to remind you is that we have E field, we have a B field, therefore we have a capacity of making work on charges, which is the essential part of the interaction. It's through this interaction, it's through this effect that we're going to transfer energy to the atomic level using light or radiation in general. The first thing we have to tell you is there is an energy density. Whatever is light occupying a space, there is an energy density involved. And this energy density, it can be calculated. We can calculate this energy density. And we can show, we're not going to do that, but you can look around any book on electromagnetism. And you're going to see that the density of energy, which means the energy per unit of volume of some space where is occupied by light, is 1/8 pi times the amplitude of the electrical field square plus the amplitude of the magnetic field square. That's a very relevant relation. And you see, basically, even though I told you already that E and B are connected to the Maxwell equation, so knowing one, you basically can determine the other. You see that you need both here. And why it's important to keep both is because they both going to interact with in different ways with the atomic system. We already know that the charge will interact strongly with the E field. The E field is what makes, by Coulomb law, a strong coupling, big force on the electrical charge. So the E field is essential for the electronic interaction. But the B field interacts quite strongly with magnetic moment. So B field will be very essential to interact with many other things, like the spin of the electron. And also the magnetic momentum determined by the orbit. As we saw in the atomic system, because of the orbit, we have a magnetic quantum number, because we have a charge in motion, and there is angular momentum, because there is mass too. Therefore, we have a magnetic momentum, as we said in the very beginning. Any charge with angular momentum somehow takes to magnetic momentum. And this magnetic momentum interacts with the B field. So when we speak about energy, we're speaking about the field's amplitude square, right? And as I said to you, to describe well the electromagnetic radiation, we must know E and B, right? Falling up to this point. Having to have E and B is not a good way to progress with the mathematics of the atom radiation interaction. We have to go a little further to simplify the way to do this. We can come back to E and B later, but we needed to come with a single vector that represents both. And electromagnetism helps us a lot in doing that. So electromagnetism helps us to understand that when we have a propagation of electromagnetic radiation, it can be described in a single vector. And they created a concept of what they call a special vector, that is the vector potential, that somehow represents E and B. And obeys the same wave equation. We did not put the wave equation here because we are not concentrated this moment to determine that this is a wave. We are concentrating getting the field, having the field, how that progress the interaction with the atomic system. Okay, so we gotta keep this in mind. So this part of the lecture is very important because from now on the next few lectures, when we speak about light, when we speak about radiation, you have to have in mind the electrical and magnetic component, so you can understand what's going on in the atomic level. And I already told you a lot about what's the transition, what's the intuition of the transition. And you have to remember that to make a transition, to make changing states, you have to put energy in the system, because each state on the atomic system, if they are not degenerated, they have different energy. So the energy will come from where? From the electromagnetic field. So always I illuminate matter, I'm putting there a density of energy. And this density of energy will be transferred to the electrons and other parts of the atom, but mostly to the electrons. Electrons are the main issue on the interaction of electromagnetic radiation with the atom. Of course, the nucleus has also a structure, has also a spin that's very important, and the interaction of radiation with the nucleus giving rise to a very important spectroscopy technique, which is the nuclear magnetic resonance, right? And we're going to see a few of that, but at the moment we are much worried about the electronic distribution and how can we deal with that. And we need a few lectures for that, because as I said to you, I prepare you to come for the point where I'm starting now, which is the interaction of the electromagnetic radiation with the atomic and molecular system. Okay, as I just said to you a few minutes ago, E and B are wonderful, but to really simplify what we're going to do, it's better to express E and B in another way. It's better to express following the electromagnetism through what we call the vector potential. The vector potential is a potential that it looks like the electromagnetic field, but it's not really exactly equal. Here we can have a vector which is composed by a amplitude, which is a complex amplitude, and a time dependence, and has the spatial dependence on this amplitude. And following the electromagnetism, if you know A, you know in any moment you can know E as a time derivative of A, and you can know B as a spatial derivative through the curve, through the cross product. So by taking the curve, by taking the rotational of the vector potential, we get the B field. And by taking the time variation, you get the E field. right? And the same way that I told you that the amplitude of the electromagnetic field, E and B, they can have a spatial dependence. Here we kept the spatial dependence as well. But you already seen that for this to be true, for any of these to be true, if we have a plane wave, if you have a radiation that's composed of plane wave, the spatial dependence of the field has to be also a kind of a trigonometrical variation in space, right? So A0, which is the amplitude, which is the spatial dependent, has to be on this form when we deal with the plane wave. And we be dealing a lot with the plane wave because the plane wave provides everything we need for most of the things we're going to do. Instead of speaking about E and B, we can speak about A. You have to be convinced by that. And how you obtain A? Well, you know, you have to go to the basis of the electromagnetism and deal a lot with that, which is not hard to do, but you have to do it. And if you do it, you're going to see that it's basically, we have a freedom to write things like this, and then through the Maxwell equations, we can find how E and B are related to this vector. There is a lot of gauges we call. Gauge to propose a potential, a scalar and a vector potential to determine E and B. You already know from electricity that to determine E, you can come with a potential, electrical potential. You know the electrical potential provides E. So sometimes in many applications we deal with the electrical potential. But we have to add a vector potential to be able to describe everything well. And when we're dealing with the light, there is no sense. We have no free charges, right? So there is no big sense to use the electrical potential. We prefer to use the vector potential in a gauge that has this characteristic. Very well. We then, instead of describing the interaction with the atomic system using E and B, we're going to use A. And or even in the electrostatic and magnetostatic kind of approach, we can also describe by by A and B. E we can describe by A and phi. Equivalently, we can describe B by A and phi. So we are doing that for the electromagnetic oscillation, but that can also be done for static kind of fields. Okay, so you see that the electrical field will be the time derivative of this. So when you do the time derivative of this, you're going to get an omega in front of this part. And because the amplitude is e to the IKR, plane wave, as we said it before, because it's the oscillation, when we're doing the cross product here, not the cross product, but the curve, when we calculate this vectorial derivative of the field, we're going to get k in front of it. But k here, we're going to have many components, so if you fix the direction of the field, we're going to have only one component here and so on. Okay. We can then express E and B with A. And when we do that, we go back to the energy density and we put in the place of A and in the place of B their correspondent expression with respect to A. And it turns out something very important, that the energy density is now expressed in terms of the amplitude of the wave vector, of the vector potential, I'm sorry. So because in the place of E will appear the omega, or in the position of the B will appear the K. Doesn't matter, but the K and omega can be connected to the velocity of light, we can convert this in a simple algebra, very simple algebra, to show that the density of energy is the amplitude times this constant, is the amplitude of the vector potential square. Normally when you have a complex field like this, the modulus of A0 square, as you know, is basically A0 complex conjugate times A0. That's the modulus, right, square of the amplitude, when the amplitude is complex. So that simplifies a lot our life, because instead of dealing with E and B all the time, we are dealing with A. And this comes in the right moment, because we now can speak about photons. Not to lose the moment, we come and say, well, what is this A actually represents physically? And remember, if I think about photons in the field, well, I know that we are thinking a lot about waves, which is fine, and that's going to help a lot to write the interaction of the atomic system with the atomic system, right? The atomic system with the electromagnetic, the interaction of light and the matter, the atom and molecules and everything. But we cannot forget that we learned in the very beginning, and this is the basis of quantum mechanics, that the electromagnetic field, the radiation, is made of photons. That's Planck's contribution, right? Planck's law. Therefore, if we have a density of energy, that density must be composed of some number of photons. If I have what we call a control volume, what volume is this? It's the volume that I'm considering the radiation there. And we learned that we have some energy per photon, which is h bar omega, right? And then if we have a number of photons in that volume, the total energy will be this number of photons, that's the number of photons, times the energy of each photon divided by the volume. So this expression is very important, because we will connect it to us through these two expressions. This can connect the amplitude of this vector, A, that we use it to determine the fields, with the number of photons. Just make this equal to this, which must be, if omega square, 2 pi c square A0 square, that's here, if that's equal to any omega, which is the number of photons. I am always keeping omega, because when we have electromagnetic radiation, we may have different components in different frequencies. And different components in different frequencies can be considered independently and add up here, right? So we consider one omega, but the electromagnetic field may be composed of many, many of those, which is fine. But then when we make equal omega squared divided by 2pc squared times the amplitude of A squared equal to the number of photons in the field, h bar omega divided by the volume, it turns that A squared is just the number of photons per unit of volume that we have, right? The number of volume is just something on the geometry, on the modes that's possible to accommodate the fields and everything. But this is important, because many, many physicists, including many in Texas, just work with, instead of working, always they're going to speak about electromagnetic radiation. They're going to create something that's a quantity that they call A and A plus. And this is somehow ways, they know that intrinsically in this, they can quantify, they can quantize it, the electromagnetic field. And this is the way that things can happen. What we have done here is quantization of the electromagnetic field. The amplitude of this vector is basically an integer number of photons. Cannot be half in here. It needs to be an integer number. All the constants here, it's not important at this point. So this A is related to the number of photons in the control volume. And this is much, much interesting. Very, very nice, because will allow us to speak about photon as well, which is important when we going to do the contest of electromagnetic radiation, light interacting with atoms and molecules. Okay, so this concept of the amplitude of the vector as the number of photons, it really turns to an important thing. It turns to tell us that as the amplitude increases, the number of photons are increasing. And normally, we going, in a more advanced quantum mechanical concepts of light and atom, they're going to transform this in an operation. It's an operation on some state that can create or reduce the number of photons in there, increase or reduce. And everything is because this relation. Everything is because here we just we express the electromagnetic field in terms of amplitude of some vector potential, and we related the vector potential with the density of energy, and we got that. Normally, we like to speak, instead of energy in the field, we like to speak about intensity. It's very common. You go and buy a flashlight and it says, well, this flashlight give you some watts of light. Or if you buy a light bubble or a light bulb or a fluorescence light or a LED, it will give you the power that puts out. And more than the power that puts out, it sometimes tells us what's the power per unit of area. And this is what we call intensity. And as you know, intensity is the flux. What is the quantity of energy per unit of time per unit of area that we are putting there. So this is densities per unit of volume. Multiplying by velocity, this comes to be energy per unit of area, because one of the length cancels. But then we have the second here, that's per unit of time. So intensity is actually the flux of energy, and will be expressed by energy per unit of time per unit of area. And energy per unit of time is what we call power. So normally we deal with this like watts per square centimeter or per meter square, or milliwatts per square centimeter or per meter square, and so on. To characterize the sunlight coming to the earth, we characterize what is the intensity reaching the earth in the surface or in the atmosphere or whatever. And as you learn from many different fields of physics, like fluid mechanics and everything, the density times the velocity gives us the flux. So if I take the density and multiply by the velocity of light, which is the propagation, I get the intensity. So actually, the intensity, which will be related to A square, right? Intensity and A square will be fully related. You agree? Because this is A square here, following this relation. So intensity and A square is fully related, and intensity is basically the number of photons delivered. I know it's expressed in energy per unit of area per time that is delivered, but actually it means number of photons. Number of photons is crucial for this whole thing, because since the very beginning of quantum mechanics, people learned that the way to characterize, to understand what we see, the interaction, the atomic system and everything, because we don't see the atom, we see the light they are emitting. That's why everything has colors. And it would be very important to know that each photon transferring energy to the atom promotes change of state, and then when returns gives the light back, and that's the way we get the light, we get everything, right? And then the number of photons will be nice, because each photon interacts with each atom in general. Sometimes you have two photons interacting with one atom, promoting transitions and everything. Okay, I think now that we made this small revision on the electromagnetic radiation, we are ready to go to the atom and put the light there. And but you know already two things that are very important and you have to keep in mind. First, we needed to think about time variation, right? We need to think about that the electric and magnetic field that compose the electromagnetic radiation are oscillating in time. And another thing is, the really basic interaction will be through a package of energy that's related to the photon itself. When we see the photon, right, when we're giving some intensity, we're giving some number of photons. And maybe if I have some atoms there, some number will disappear. And then comes the more interesting thing. Sometimes I put light, I have some number of photons, and on the other end, I get more number of photons. If there was energy storage in the matter, in the atom, or molecules, it's possible that the perturbation introduced by the fields of the light, or the radiation in general, will cause remotion of photons, of energy of the atomic, of the atom and molecules, through the emission of photons, right? So all those phenomena are present, and now we have the basic elements to understand what's going to happen in this interaction. Okay, you see, this is a very nice field, and I want to go in detail. And we're going to need more than one lecture to tell you about all this interaction, everything. So on the next lecture, we're going to continue from what we stop here to be able to tell you now what is essential. How can we write the wave equation? How can we know how the energy of the electron in the atom is changing in the presence of light? How can we do that? And what are the consequences, right? What are the consequences of shining light into a system that can have only a few configurations of charge? Which are the states, which are the wave function? How they talk each other now? Is that allowed? Always going to happen? That's what we're going to see in the next lecture. See you then. Bye-bye.